record. So I'm recording now. It's an algebra tute today. So let me show you what we can discuss. So believe it or not, in this tutorial, we are supposed to discuss all of the questions for chapter 2, which is a pretty long section. Now, I have done some of these questions already in Monday's tutorial. So there are a lot of questions. We don't need to do them twice necessarily, but I think I'm going to talk about the dot product, the cross product, and the scalar triple product. They're the main 3 parts of this section. Okay, so I wanted to talk about this one here. Okay, this is an interesting question because you're using the dot product to prove something of a geometric nature. So let's have a look at that. And one of the difficulties with these questions is students, they're not quite sure where to start. So we're in chapter 2, page 73, Chloe. So go and check it out. That's where we're at. So let's have a look. Let's have a look. So I'll stop sharing that and I will share my document camera. So here comes the Chrome tab. And today I'm using Sharpies. Okay, so let me know what you think of the writing. Do you have Sharpies? I think they're pretty good so far. So what I'm going to do is I'm going to draw a square. Okay, so here's my badly drawn square. I'm going to label the corners. And what we're asked to do is to show that these diagonals intersect at right angles. Okay, and in particular, we are asked to use the dot product. Yep. Yeah, Shujun, yes, we're doing algebra today. Yep, it's an algebra tutorial today. Yeah, Shinyi is on the chat. Yes, I think this is what we're asked to. This is what we can do. We can show that the vector joining these points dotted with the vector joining these points is just 0. So you're absolutely on the right track there. Okay, so what I'm going to do is just outline what our strategy is, right? So let's look at this vector and show that their dot product is 0. Okay, I've got mine slightly around the wrong way from the chat, but that's fine. That's not a problem. So the diagonals, diagonals intersect at right angles. Okay, so this is a square, so that side, that side, that side, and that side are all equal in length. Okay, all right. So what we're going to do here is we're going to use the triangle rule of addition. We're going to express the diagonals in terms of the vectors making up the sides of the square. Okay, so let's look at AC. So let's look at this diagonal first. I'm going to write that in terms of the vector AB plus the vector DC. Okay. Okay, so that's just the triangle law of addition. So to go from there to there, we go from here to here, and then here to here. Okay, and there's a little algebraic check just by putting your finger in there, right? So AC, AC. I need a fatter finger, thumb, AC, right? Okay, now you see it, now you don't. All right, so that's one, and now we've got that vector. Let's express this vector in terms of these two sides. So dB will be dA plus AB. Okay, now when we take the dot product of these two things, we're going to want to get some cancellation, as you can see. So what I'm going to do is just express this in terms of this first part in terms of dA. Okay, you don't have to do that up here, but it's just nice to do that. So now when we take the dot product of these two things, we're going to get the cancellation that we want. Hence, let's do it. Okay, so we've got this dotted with this. That's a D. And you know that the dot product, you can expand this like you would normally with regular multiplication. So this times this will give you negative dA squared. So when you dot product something with itself, you get the square of the length. And I've just put the negative sign out the front. And so you do this one and you'll get negative dA dotted with AB. And then so we've done that and that. Let's do this one. Yep. And this times this. Oh, okay. I probably should have put another one in there, but that's okay. Okay, so what am I missing here? DC, you can see DC is the same as AB. So if I really wanted to be a little bit more careful here, I would have put that up there. Okay, and then done it in here, but I can still fix that up, right? Okay, so AB is just equal to DC. So this thing is going to become DC squared. And in here, this is going to become AB. So this thing and this thing will cancel out. So let me just write that in. Okay, so that's going to cancel with that. And who can tell me, why are these two things equal? Can anyone tell me why this plus this is actually 0? Anyone in the chat? Anyone? Smash that chat button. Let me know. Why is this plus this equal to 0? It's a squared. CG, yes, you rule. Okay, the sides are all equal. Okay, so this and this are just 0. Okay, so we know that the dot product's 0, hence there is a right angle between the diagonals. Okay, so I've just squeezed it in there. Okay. Okay, Fard, good question, right? So you can see here, Fard, I've gone up here, AC. Okay, it's a really good question. So to get from A to C, I'm going to go from A to D and then from D to C. Do you understand that first part, Fad? Okay, so what's AD? AD is the same as negative DA, right? So all I've done there is I've changed the direction. Yep. And then DC is the same vector as AB because they're parallel and they're the same length. Okay. Sichuan, yeah, you can use that if you want to. I have seen that. I like labeling the corners first, but it's up to you. Okay, it's up to you. There are many ways to solve this problem. So it's up to you. All right, good job, Fad. That's excellent. Okay, so that is question 6. And you can, there are simpler ways to do it. Okay, there are simpler ways to do it. Okay, let's have another look at another question. So I'll go back to the sheet. And here it is. All right, so that's dot product, yeah? I think what we might do is look at the distance between a point and a line. Now, this involves the projection of one vector on another. And I think it's fair to say that a lot of students struggle with this because it's very geometric. Okay, so let me show you one that I've done earlier, and you should be able to get a good idea of what's going on, right? So I'm just going to show you one that I did in a previous class, so I can share my screen. You've got a point, and you've got the equation of a line, and you want to find the distance between that point and that line. So it's like the shortest distance. Okay. All right. So let me share again. All right. So here's one that I've actually completed earlier. So don't worry about this stuff yet. Okay. But here's a line, right? Here's a vector that's parallel to the line. It could be pointing in the opposite direction, but who cares really? Here is a point B and a point A that's on the line, and we want to work out this distance here. You can see a little right angle there. Okay, so in these type of questions, what you're trying to do is compute the distance from B to P, and you don't know what P is ahead of time. Okay, so that's the idea with these kind of questions. Okay. So that's really what we're trying to. B is a known point, A is a known point, V is a known vector, but P you don't know what it is. Okay. All right. So the easiest way that and don't worry about this, by the way, the easiest way to think of this, in my opinion, is just to use Pythagoras. Let me sort of guide this. Okay. Use our old friend Pythagoras, or if you're in China, Hertz theorem, right? So we know that we've got a right angle triangle. If I draw a little line from here to here, and I can work out the length AB because I know A and I know B. I want to find out that length. And if I can find that length, A to P, then I can use Pythagoras. Okay? So this is easy. This is a little bit harder to get that length there. Okay? So how can I work out AP? Well, the vector AP is just the vector projection of this vector on that vector V. Let me say that again. The vector AP is just the projection, the vector projection of this vector on that vector there. That actually gives you the vector AP. Okay? So I can actually work out its length and whatnot, and then apply this Pythagorean formula. Okay? All right, so here's some of the notation. This vector is just the projection of AB on V. And I know that that involves a dot product and some lengths, and this is just a unit vector in the same direction as this V vector. Okay, so it's a special thing. You've got this thing times a special vector. All right, so all we've got to do is compute this, but we actually don't want AP, we just want the length. So if you go in here and calculate the length, this unit vector disappears because it's length 1, and you're left with this. Oh my goodness. Let me move that down a bit. Ja. Okay. Fei Wei, V is shorter than AP. In this picture, yeah, but it doesn't matter how long or short V is. Yeah. So it doesn't matter how long or short V is. It's still the projection, right? Yeah, good question. Okay, so let's find the length of this. This has length 1, so all we do is we get this, involves a dot product. Now, for our question, this is the data. A is this point, B is this point, and V is this vector. That's all we need. Okay, that's all we need. Okay, so I'm going to compute AB there. I'm going to take the dot product of that vector with V, and I'm going to look at the length of V. Hi, Fiona, welcome. Okay, so that's what I've done in the next bit. So the vector from A to B is just this vector, the vector for this minus the vector for this. So you get this, and I need the length of V. Okay, so I've done that. How do you do that? You square the components, add them together, and take the square root. All right, we're almost finished. So I want to get this. If that's AB, then the square of the length, you square the bits and add them together. You get 110. And using this up here, I want the dot product. So the dot product of AB with V is just that times that, plus that times that, plus that times that. We're taking, because it's a length, we're taking the absolute value, and you divide by the length of B. Okay? All right, so I've got this. All I need to do is square it. So you get 61. So it's going to be that minus that put into there. Okay. All right, Fad, can you tell me a little bit more about your question there? Can we use the projection formula first and then use the distance formula? Yeah, you can. I mean, ultimately, it's you're applying Pythagoras. That's ultimately what you want to do. Okay, so you can actually compute, excuse me, all of these things first, and then use Pythagoras. Does that make sense, Fad? Yeah. I've just tried to explain what's going on here with a picture first. And, you know, Pythagoras is usually simpler than all this other stuff. So I try to start, because I'm a simple guy, I try to start with the most simplest explanations. Okay, so the answer is just 7 units. So the distance from here to here would be 7 units. Okay. I'm loving the questions in the chat, everyone. I'm really enjoying that. So if I was to go back to the next question, I won't do the next question, but let me just discuss it with you. Sichuan, you don't understand the length of AP. So AP, the vector AP is just the projection of this vector on this vector. That's actually how we geometrically define it. Okay. Hey, Floyd, welcome. Okay. So this vector, the vector projection of this vector on this vector is the vector from A to P. Okay. And once you know the vector, you can calculate its length. So that's for the vector. If you take the length of that, that's 1. This is 1, and you're just left with the absolute value of that. Okay. So Sishwan, it's important to understand how we define the vector projection, but then also how to get the length of this vector. Okay. All right. Awesome. Loving it. Keep the questions coming, people. Okay. So if I was to look at part B, I won't do it, but we can just talk about it together quickly. So here you can see part B is almost the same as part A, except the equation of the line is different. So who can tell me in the chat what is a point on this line? What would be our A point for this line? Can anyone tell me? 1, 2, 3. Yes, thank you. Thank you, Lucas and Fad and Feyui. And what about a vector V that is parallel to the line? What would that be? Can anyone tell me in the chat? Smash that chat button. Let me know. I've forgotten, right? Yes, thank you. Okay, great. So you would just repeat the process of part A in part B now that you know all the data. Okay, now that you know all the data. So that's great. Okay. Let's have a look at another question. So that's mostly dot product. Let's have a look at cross product. Okay, so we've got 2 vectors here, A and B, and they want us to find the cross product. Now, when people see the cross product, sometimes they get angry, right? Like sometimes maths makes people angry. They get really cross and angry. But I'm hoping the cross product is just friendly and easy to do for you. Let's discuss what it means and how you can visualize it. So you start with 2 vectors. What does this operation actually mean? Okay, so did somebody say GeoGebra? Let me show you what I've done ahead of time with GeoGebra. Because if you can understand this, then you have a really good understanding of the cross product. Okay, so I've got 2 points in 3-dimensional space, okay? A and B. So this is from question 14, part A. All right, so A and B. And let's put in some vectors, some position vectors, okay? I don't want to make you dizzy here. Oh, come back. All right. All right, so if I take the cross product of these 2 vectors using GeoGebra, what happens? Well, I'm glad you asked. Kapow! We get a 3rd vector. We get a 3rd vector. Now, what is the relationship between the 3rd vector and the other 2 vectors? Well, kapow! You put the plane in that's spanned by vectors A and B, and what's that 3rd vector doing? It is normal. It is normal to both the vector A and the vector B. So essentially, it's normal to the plane. Okay? So geometrically, that's what a cross product gives you. Yeah, orthogonal, fair yes. You can use the word orthogonal, normal, or perpendicular. They're all correct. Okay? Now, you can see here, if I do the cross product the other way, watch what happens. Bam, 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 bam. The new vector points in the opposite direction. So order is important, okay, when you're doing these calculations. Okay, so let me go back to my document camera and we can do a problem. All right, so let's consider, this is 14A. All right, so we've got two vectors. A is 0 to -4, and the vector B is 1, 3, 2. Okay, so the way that I like to compute these things by hand, and of course you can use whatever method you like, is through what's known as a determinant. So let me show you. As some of you know, I've lectured this course many times, and what I like to do here is to use a determinant. Okay, so let me know if this is familiar. So you write ijk along the top, and then you write these things as rows. Okay, so let me know in the chat if this is familiar or not, because I do know some lecturers do it differently. Okay, so let me know. And the idea is to start in this top left-hand corner and you expand the thing along the top row. Okay, all right, thanks, Jason. Now, if I have a 2 by 2 determinant, that's just defined as this times this minus this times this. Okay, it's like a definition. All right. Now, you might think, well, why do I want to learn this? I just want to learn the formula, brah. That's okay too. But the nice thing about this method is you'll never forget it, and it's useful for when you study matrices. The last part of this course is about matrices, and you look at determinants. Okay, so this is called a determinant. So what a lot of students see as a good thing is learning determinants now. So in week 10 or week 9, when you do matrices, then you already know what they are. Okay, so we can play a little game of cover up. So I start up here. I is in the first row in the first column. You cover those up, and then you multiply I by the determinant of what's left. So that times that minus that times that. And then you move over to J. Cover the row and the column, that times that minus that times that. And then K, that times that minus that times that. And the last thing is you alternate the sign. So it goes positive I, negative J, positive K. All right, I'll talk about that in a minute. Let me just write it out. All right, so one way of looking at this is to go, right, I times that. Okay, and then J times the determinant of that, but we alternate the sign. So it's that. And then we alternate the sign again. Okay, 0, 2, 1, 3. Now, some of you will be thinking, Professor, why do we alternate the sign? I will discuss that in a minute. Okay. Okay, so let's go up here. 2 times 2 minus -4 times 3. So you're going to get 4 plus 12. Okay, over here, you've got 0, 0 minus -4. And lastly, 0 minus 2 times 1. Okay. So now you just need to simplify these things, right? So that's going to be 16i minus 4j minus 2k. If you want to write it as a column, feel free. Okay. So one of the key questions here is, why do you alternate the signs? Well, the reason is that you want the things to be consistent with the formula, right? The formula, which is a horrible formula for the determinant, okay? And so putting that negative sign there means that you can still use the determinant and you get the right thing, okay? You get the right thing. Fud, not, yeah, it's 4 minus -12i. So that times that minus that times that. Yeah, you got it. Yeah. Okay. So I probably should have put 4 minus -12 there. Yeah, I know. I tend to make a lot of mistakes with these things, but you know, hopefully you won't have to worry about it. Okay. There we have it. Let me just zoom out for a bit. There, that's better. Okay. So that's a pretty easy one. And the nice thing about it is you get to understand a determinant, and they're going to be useful in like week 9 or week 10. All right. What else have we got here? Let me have a look. Let's go to the scalar triple product. Okay. So I'm just going to look at my PDF here, and I'll bring that up now. All right, Sichuan, you have a J, that times that minus that times, no, I think it's correct. It's correct. If you want to do the calculations, feel free to check it. So if you have a different method, I would suggest that you do it using your method and see if you get a different answer. Does that sound okay? Because I'm just checking it now, and it looks fine to me. That times that minus that times that, and you have the negative. Okay. Oh, sorry, I've got the PDF up there. Okay, so have a look at it, Sichuan, and let me know if you still have a problem with it. All right. Scalar triple product. Find the volumes of the following parallelepipeds. So some people say parallel pipes. I say parallelepipeds. You can say it however you want to say it. Okay. Now, the scalar triple product can be used to measure the volume of a box, right? So let's do this problem. We can talk about the scalar triple product. Now, the scalar triple product looks a bit like the cross product, but there's just something else in there that we have to think about. Okay, so instead of having I, J's, K's there, we have something else. All right, so let's have a look at 25. All right, here we go. All right. So we have this parallel pipette. So consider these vectors. And these vectors kind of form the vectors that span the parallel pipette. So I'm just going to label them in this way. Okay. Now, the volume of a parallel pipette with these sides is just this. Now what is this? Well, it's just the cross product done first and then the dot product. But you can write this in terms of a determinant. Okay, so notice I don't have ij's or k's there. I've now got the entries from the vector A. Okay, and you can do this like the same way by expanding it and covering up and doing all that sort of stuff. But actually, there's an even quicker way of doing this problem. Okay, you can actually expand it in different directions. But so let me show you, because we're calculating volume, the order here doesn't matter, right? The order here doesn't matter. So I'm going to do this a slightly different way. I'm going to put this vector up the top. Okay, so I'm just going to do it like this. Okay, why am I doing that? Because with the 0 up the top, it's easier to expand. And I'll show you what I mean. Okay, you don't have to do it like this. You can do it like this, no problem. Okay, having that 0 there is really nice, because if we expand along the top row, then 0 times that is always 0, right? So 0, it doesn't matter what these things are. If I've got a 0 up there and I'm multiplying it by that determinant, it's always 0, okay? Well, Shujun, it doesn't matter. Like if you take the volume of a box, right? It doesn't matter which way you do the calculations. Here we're just interested in the absolute value of this thing, right? So it doesn't matter which way I do it. You're always going to have the same volume. You're not changing the volume. Does that make sense? Okay, so it doesn't matter which way you do it, which side you use. Okay, so the first thing is 0. You change the sign, so cover that up. 4, 2, 2, 3. 1 times that determinant. 4, 1, 2, 1. Okay, so that's easy. This is easy to work out. You're going to get -2, that's going to be 12 minus 4, which is going to be 8. That's going to be 4 minus 2. So, oh yeah, hang on. So I'll put these in here. So we're making the absolute values. Okay, there. So you're going to get -16 plus 2, -14. There you go. Okay. So what I'll do is, just to make it a bit easier, I'll put absolute values around here too, just to make sure that that's, so I'm taking the absolute value of this scalar triple product. I think that's probably a better way to write it. Yeah, CG, yes. You're absolutely right there. Imagine a box, the volume will not change if you flip the sides around or you change it. Yeah. Yeah, Sinji, you are asking, is A cross B, it's the area, right? So if you have, that's a really good question. Let me know if people need to see this. So if you have, say, a vector there and a vector there, and you draw in a parallelogram, right? So the area is just the length of the cross product of the two vectors. Okay. Yeah, and so the argument, like the way you get this is, yeah, you use this as the base, and then you can get the height and stuff like this, and you involve projection. Okay, definitely involves projection. Okay. All right. Let's have a look. Oh, okay. Let's have a look at one more. Let's look at 26. So I'll just share the PDF again. Here we go. I can bring it back up in a minute. Okay. So last question. Show that these 4 points are coplanar. What does coplanar mean? Anyone want to tell us in the chat? What does coplanar mean? I'm confused. I have no idea. What does coplanar mean? Any idea? Yeah, they all lie on the same plane. Yes, Feiwi, yes. So they live on the same plane, just like collinear. All the points lie on the same lines. All right, show that these 4 points lie on the same plane. Let's have a look at that. Okay, so here's the previous question. I need the hotkeys to go between cameras, right? It's very slow. So here's the previous question, and here is the upcoming question. Okay, so how do we know that 4 points are coplanar? Well, what you can do is you can assume that the vectors involved form the sides of a three-dimensional object like a box or a parallelepiped, and actually show that these calculations give you zero. Okay, if a box has got zero volume if and only if one of the measurements is zero. Okay, and if that's the case, all the points lie in the same plane. So let's have a look. Here's one that I've done earlier. So here are your 4 points. So this is just the origin. That's like an O. They're zeros. So we know that this thing, if this thing is satisfied, this condition is satisfied, then the volume associated with the box has to be zero. And that's only true if these things are all in the same plane. So you get a two-dimensional shape, not a three-dimensional solid. Okay, so I can just think of these as position vectors. So you write them as rows and you just expand them out, right? So you start here, cover up 2 times this determinant, which is that, minus 1 times that determinant, plus 3 times that determinant. Okay. So, you know, you simplify this and you end up with 0, and you make a conclusion, which is nice. Okay. Now, a good question here is, like, we're doing this using determinants. Is it okay to do the cross product separately and then the dot product? Can anyone tell me? Like, could I work out the cross product of this and this as vectors, and then take the dot product separately with this vector up here? Is that okay? Who can tell me in the chat? Like I don't have to just do this, or I can work out the cross product first and then do the dot product separately. Yeah, it's possible. It's possible. Yeah, it is. It takes longer, but it's possible, right? And that's another advantage of this determinant approach. All right, Fei Yui, the vectors all start from the same point. Yeah, for the pictures in this, to get the box, you sort of have your, you have a vector like this, a vector like this, maybe another vector like this. And once you have that, then you have all the sides of your parallelepiped, right? Yep. So that might be the origin there. Does that make sense? Okay, it's a pretty bad drawing, but you get the idea, right? Okay, folks. Are there any last questions? Because we've got about 1 minute. Any requests for music for next time? Just let me know what you want. I hope Maple TA isn't painful. Again, I know sometimes it's painful. Just keep going. The lab test 2 practice has been released, right? Am I right? Lab test 2, right? It's been lab test 1 has been released. So my my advice is to practice it. There won't be any surprises. Yeah, that's good. Okay, so in the 1 minute that I've got left, let me look at the right-hand rule. Okay, here's the vector A. Hello. Here's the vector B. Hello. It's my right hand. When you cross A with B, it goes in the direction of the thumb. That's the right-hand rule. Whew. Okay, Shujun, that's the point. This finger is the first vector. This finger is the second vector. You put your thumb up, that's where the cross product vector points. You got it? That is the right-hand rule. Yeah. Woohoo. All right. I am heading off. Yes, Shishuan, yes, you can find all the questions on Maple TA. Thank you, everyone. Goodbye. We'll see you next week. Same time, same place. I'm really enjoying these tutorials. I hope you are too. And, see you later. Bye-bye. 再见. See you next week.